Einstein quantum. Albert Einstein, the man who redefined space, time, and gravity, the architect of our modern understanding of the cosmos, had a ghost that haunted him. It wasn't a spirit or a phantom, but an idea. An idea so profoundly strange, so contrary to every intuition about how the universe ought to work, that he gave it a now famous name: spooky action at a distance. This spooky idea was quantum entanglement, and Einstein's battle against it would become one of the most significant intellectual struggles in the history of science. To understand his deep-seated resistance, we have to step inside his mind and see the universe through his eyes. For Einstein, the universe was, above all, sensible. It was a grand cosmic clockwork governed by elegant, predictable laws. His theory of relativity was the crowning achievement of this worldview. It established a fundamental speed limit for the cosmos, the speed of light. Nothing, absolutely nothing, not matter, not energy, not even information, could travel faster than light. This principle wasn't just a rule, it was the very foundation of causality. An event here could only affect an event there after a certain amount of time had passed, the time it takes for a signal to travel between them. This is the principle of locality. Think of it like a game of cosmic billiards. One ball can only affect another by directly hitting it. It can't mysteriously cause a ball on the other side of the table to move without some physical interaction traveling between them. This, to Einstein, was just common sense. But there was another pillar to his worldview: realism. Realism is the simple, intuitive idea that objects have definite properties that exist whether we are looking at them or not. A coin flipped and covered by your hand is either heads or tails. You don't know which it is, but the property of headsness or tailsness is a real objective fact waiting to be discovered. The moon is still there, existing in its specific location, even when no one is observing it. These two principles, locality and realism, formed the bedrock of Einstein's physical intuition. They described a universe that was predictable, objective, and orderly. And then, along came quantum mechanics. The new theory was a wild success, predicting the behavior of atoms and particles with astonishing accuracy. But its core principles were deeply unsettling to Einstein. It described a world of probabilities, not certainties. A particle didn't have a definite position until you measured it. Instead, it existed in a cloud of possibilities. To Einstein, this was an admission of failure. He famously declared, "God does not play dice with the universe," believing that the probabilistic nature of quantum theory was simply a sign that it was an incomplete description of reality. He was convinced there must be some deeper hidden information, what physicists would later call hidden variables, that determine the outcomes we see, restoring the universe to its deterministic, clockwork glory. Nowhere was this clash of worldviews more apparent than with quantum entanglement. The theory predicted that you could create two particles, say two electrons, in such a way that their properties were intrinsically linked. For example, electrons have a property called spin, which, when measured, is either up or down. If you create an entangled pair, they will always have opposite spins. If one is measured to be spin up, the other at that very same instant will be spin down. If the first is spin down, the other is instantly spin up. This, in itself, isn't so strange. Imagine you have a pair of gloves. You put one in a box and the other in a second box without looking. You mail one box to your friend on Alpha Centauri 4 light-years away. When you open your box and see a left-handed glove, you instantly know, without a shadow of a doubt, that your friend has the right-handed glove. There's nothing spooky about that. The gloveness was determined from the moment they were packed. This is the kind of explanation Einstein could accept. This was a hidden variable theory. The information was always there, just hidden from you. But quantum mechanics claims something far more bizarre. It said the particles do not have a definite spin until one is measured. They exist in a state of pure potential, a superposition of both up and down simultaneously. The moment you measure one particle and its state collapses into, say, spin up, its entangled partner, even if it's on the other side of the galaxy, instantly collapses into the opposite state of spin down. This isn't just revealing pre-existing information like with the gloves. It's as if the act of observing one particle creates the reality of the other, instantaneously, across any distance. This is what horrified Einstein. This was his spooky action at a distance. It seemed to violate the cosmic speed limit, the principle of locality. How could the measurement of a particle here have an instantaneous effect on a particle light years away? It was a direct assault on the very fabric of space-time as he understood it. In 1935, along with his colleagues Boris Podolsky and Nathan Rosen, he formalized this objection in a famous paper known as the EPR paradox. They argued that since this instantaneous influence was absurd, quantum mechanics must be incomplete. There had to be hidden variables, just like with the gloves, that predetermined the spins of the particles from the moment of their creation, preserving both locality and realism. For decades, this remained a philosophical standoff, a deep chasm between two competing views of reality. Was the universe the sensible, local, and real place Einstein believed in? Or was it the interconnected, probabilistic, and downright spooky place that quantum mechanics described? The debate seemed unresolvable, a matter of interpretation. But what no one knew at the time was that a brilliant physicist, decades later, would find a way to put this philosophical question to the ultimate test and force the universe to show its hand. Non-local universe proof. For nearly 30 years, the debate sparked by Einstein, Podolsky, and Rosen remained stuck in a philosophical quagmire. It was Einstein's powerful intuition versus the strange but successful mathematics of quantum theory. The hidden variables he proposed seemed like a perfectly reasonable way to save common sense. How could you ever prove they didn't exist? It seemed impossible. You could search for them forever, and upon finding nothing, critics could simply say you hadn't looked hard enough. The argument was at a standstill until 1964, when an Irish physicist named John Stuart Bell came along and changed everything. Bell wasn't trying to prove one side right or wrong. He was simply fascinated by the foundations of quantum theory and took Einstein's objections seriously. He wondered, if this hidden information, these local hidden variables, actually existed, would they have any observable consequences? Could you design an experiment that could tell the difference between a universe with hidden variables and one without? The answer, it turned out, was a resounding yes. Bell's genius was to translate the philosophical debate into the language of mathematics, creating what is now known as Bell's theorem. The details are mathematically complex, but the core idea is beautifully simple. Bell devised a statistical test. He imagined measuring entangled particles not just in one way, but along several different angles. He then calculated the maximum level of correlation you could possibly expect to see between the measurements. Of these distant particles, Einstein was right. If the universe was governed by local realism and hidden variables. He established a hard limit, a mathematical boundary now known as Bell's inequality. Think of it as a line in the sand. If local realism holds true, the results of any real-world experiment measuring these correlations must fall below this line. However, Bell then calculated what quantum mechanics predicted for the same experiment. The prediction was startling. Quantum mechanics said the correlations would be so strong that they would cross the line, violating Bell's inequality. Suddenly, the debate was no longer philosophical. It was a concrete, testable prediction. Bell had provided a recipe. Build an experiment, measure the correlations between entangled particles, and check the numbers. If they respect the inequality, Einstein's intuition about a local, predetermined reality wins. If they violate it, the universe is fundamentally non-local and spooky in exactly the way quantum mechanics describes. The gauntlet had been thrown down. In the 1970s and 80s, physicists like John Clauser and Elaine Aspect took up the challenge. They performed pioneering experiments using entangled photons, and time after time, the results came in. They consistently violated Bell's inequality. The data sided with quantum mechanics. It was a stunning confirmation, but a sliver of doubt remained. These early experiments, for all their brilliance, suffered from potential loopholes, tiny cracks in the experimental design through which local realism could, in theory, sneak back in. There were two major culprits. The first was the locality loophole. Perhaps the particle detectors were not separated far enough or the measurements were not fast enough. This left open the possibility that some unknown signal traveling at or below the speed of light could be passing between the two detectors, telling them how to behave and thus faking the strong quantum correlation. The second was the detection loophole. The detectors of the era were inefficient. They missed many of the photons. What if the experiment was only detecting a biased sample? Perhaps the universe was only showing us the particles that happen to agree with quantum mechanics, while the ones that would have confirmed local realism were simply not being counted. For decades, closing these loopholes simultaneously in a single, definitive experiment was the holy grail of quantum physics. Then, in 2015, the breakthrough finally came. A team led by Ronald Hansen at Delft University of Technology in the Netherlands performed a landmark experiment. They entangled the spins of two electrons trapped in diamond crystals located in separate labs 1.3 kilometers apart. They used incredibly precise timing and random measurement settings, ensuring that no light-speed signal could possibly travel between the two labs in time to influence the outcome. They closed the locality loophole. And by using highly efficient measurement techniques for the electrons, they also closed the detection loophole. The world held its breath. The experiment ran, the data was collected, and the result was announced. The results were unambiguous. Bell's inequality was violated every single time. Since then, other even more rigorous experiments have confirmed this result beyond any conceivable doubt. The verdict is in. Einstein, the titan of physics, was wrong on this point. The universe is not local. His spooky action at a distance is not a flaw in the theory, it is a fundamental feature of reality. The properties of an entangled particle are not predetermined. The universe plays dice. And when it does, the outcome of one roll can have an instantaneous, unbreakable connection to another roll happening light years away. This discovery shatters our classical view of the world. It tells us that, at the most fundamental level, the universe is not a collection of separate objects, but a single, interconnected whole. This doesn't mean we can send faster-than-light messages. The randomness of the outcomes prevents that. But it does reveal a layer of reality, a profound interconnectedness that defies our everyday experience of space and separation. The spooky curse Einstein feared turned out to be one of the deepest truths about our cosmos, proving that reality is far stranger and far more magnificent than even he ever imagined.